waves here, waves will start off from, Walaikum Salam. Waves starts off from types of waves we did in the last class. There are two types of waves. One is your progressive wave, one is the stationary wave. Progressive waves are the ones that can travel and are divided into two subcategories, one being transverse wave, one being longitudinal wave. Okay? Further on, we discussed that the transverse wave would look somewhat like this, while the longitudinal wave looks somewhat like this, right? Thereby establishing the fact that in a transverse wave, the particle movement is perpendicular to its wave motion. Whereas in a longitudinal wave, the particle movement is parallel to the wave motion. In AS, there is specifically a different type of wave called stationary wave. That's in the course. A stationary wave is a type of wave that is confined within a loop. Let's say for a minute, this is a rope, right? I push the rope up and down such that it produces a wave. The wave will touch the wall and reflect back, thereby coming back to its original shape, that is a straight line, meaning to say it cancels off, right? When it cancels off, definitely there is no net transfer of energy. And that is why we say it's, we establish this fact here, right? Properties of progressive waves. Progressive waves will undergo reflection. When they undergo reflection, their speed, frequency, wavelength all remain unchanged. Whereas in refraction, when it moves from a deep area into a shallow area, you need to understand that the wavelength decreases. And according to V is equals to F lambda, when the wavelength decreases, it causes the speed to decrease. Please note that the frequency should stay the same because that is an identity of the wave. Whereas from shallow to deep, the wavelength increases and therefore the velocity will increase. Frequency stays the same. Waves undergo a few more properties, one of them being superposition. Superposition is basically two waves. When they meet at a common point, right, they will either add up or subtract off. Before we move on, in the last class, we established what two waves in phase with one another would mean. For example, if this is a wave, right, the maximum positive amplitude is called a crest, right? So when you compare two crests, these 2 points are called in phase to one another. And when 2 points are in phase to one another, they have a part difference of lambda in between them, right? Let's say if I am comparing this point, this crest to this crest, right? So from here to here would be 2 wavelengths or 2 lambda. This distance is called the path difference. Out of phase points are the ones that behave in the opposite manner to one another, right? So basically, moving forward in a progressive wave, points whose behavior is identical to each other are classified as in phase points. For example, one crest when compared with another crest, or one trough when compared with another trough. These concepts do not just restrict to crests or troughs. There can be any point in between, right? Moving forward, for points to be in phase, they must establish a part difference of lambda, 2 lambda, 3 lambda, 4 lambda. If you check on from here, the difference between one crest to another crest, the consecutive one was 1 lambda. Whereas from the first crest to the third crest, your wavelength was 2 lambda. So these points have part differences as 1 lambda, 2 lambda, 3 lambda, and therefore these are in phase with one another. Okay? Moving forward, there's another concept called phase difference. Once you work out the part difference, you simply multiply the value by 2, and in place of lambda, you replace pi, and that makes it phase difference. By the way, phase difference is the distance between 2 points in terms of their angles, right? Whereas part difference is the distance between 2 points in terms of their distance, right? Phase difference को आप लोग in terms of angles भी बात कर सकते हो. Like you could say it's the angular difference between two different points. Let's say if I were to draw a wave, right? When one complete wave is formed, right? It covers 2 pi or 360 degrees, right? Let's say another wave is forming here. If I were to compare this point with this point, since it is in terms of angles, I will call this difference as a phase difference, right? Let's say I am moving a little ahead from here till this point, and from here I am moving ahead again to this point. If you were to compare this point C with the other C, the crest with another crest, and you were to give your answer in terms of phase difference, you would simply state 2 pi or 360 degree. Basically, the angular difference between the 2 points is the phase difference. In terms of angles, you call it phase difference. In terms of distance, you call it path difference. But moving forward, for points to be in phase, they must establish a path difference of lambda, 2 lambda, 3 lambda, and the corresponding phase difference. Just multiply. Let's say you had lambda, a path difference of 1 lambda. To calculate its phase difference, you multiply this value by 2, and in place of lambda, you place pi. If your path difference is 2 lambda, your phase difference should be 4 pi. For 3 lambda, it should be 6 pi, and so on. Moreover, points whose behavior is exactly opposite to each other are classified to be out of phase with one another. These points must establish a path difference of half lambda, 3 lambda, 5 upon 2 lambda, basically in terms of decimals. 0.5, 1.5, 2.5, 3.5, and so on. And a corresponding phase difference. Again, to calculate the phase difference, you multiply the value by 2, the corresponding path difference value, and in place of lambda, you place the pi value. Again, just a revision. Path difference is the distance between 2 points when measured in terms of lambda or the distance. Phase difference is the distance between 2 points when measured in terms of degrees or radians. Principle of superposition. When two waves meet at a common point, right, they will either, the resultant is basically the sum of the total displacements, right? You need to first understand, let's say, when two waves are in phase to one another, they will simply add off. Whereas when two waves are out of phase to one another, they will simply subtract off, such that there is nothing left, right? It can vary from case to case. Had it been 2A and this being minus A, your total displacement or your resultant displacement that you would have been left with would have been 1A. Superposition leads to interference. There is constructive interference for in-phase points. There is destructive interference for out-of-phase points. Moving forward, again, according to principle of superposition, whenever two or more waves meet, by the way, they should be of the same type or overlap with each other. The total displacement due to these waves is the sum of their individual displacement. Superposition will always lead to interference. For constructive interference to occur, your points must be in phase and then superimposed. For destructive interference, out of phase points must superimpose. Let's say, for example, I have a question, a wave from point X, a wave travels from point X to point P such that it covers 16 meters. The wave has a wavelength of 2 meters. There's another wave from point Y travels to point P such that it covers 15 meters and it has a wavelength of 2 meters. Now, whenever a wave travels, it has its own specific path. The wave traveled 16 meters. I need to check how many wavelengths can cover this distance, or you could say in simpler terms, how many waves would be consumed in traveling this distance, and this value is called its path. This would give you a value of 8 lambda, meaning to say 8 wavelengths are required to cover this distance by this specific wave X. For wave Y, similarly, you take 15 meters divided by the wavelength of the wave, and that gives you a path of 7.5 lambda. Now at point P, both of these waves are meeting. Both have their own specific paths. So to calculate the path difference, I simply subtract the two values. Right? 8 lambda minus 7.5 lambda. You will understand the fact that it is coming out to be half lambda or 0.5 lambda, which tells me that these waves are out of phase and therefore they will meet destructively. And when they meet destructively, their amplitudes will cancel off. Let's say you are given the amplitude AA. Since they are meeting destructively, you simply subtract the two amplitudes and you will realize that the wave gets destroyed. Had they asked you the phase difference, you would have simply stated for half lambda, it would have been 1 pi. In this question, they have given you the wavelength 30 millimeter. They've given you the amplitude at point X. They've also given you the amplitude at Y for wave Y and its wavelength and the corresponding distances, right? Please understand that this is 140 and it is equally distributed. So the distance from X to point midway through should be 70 millimeter. I want this distance. I can use Pythagoras theorem, but for that, you need to understand that from 514, which lies somewhere till here, I need to subtract 70 to come with a value somewhat here. And when you subtract the two values, this distance comes out to be 444. You are provided with the horizontal distance. You can apply Pythagoras theorem and you'll get an answer of 923.7 millimeter. Similarly for Y, there's an additional 70 millimeter downward, right? you will extend this wave till point Y such that it makes a right angle triangle here, right? This was 514 till here. You add off 70. This one was 8110. And from Pythagoras theorem, you will realize that this distance comes out to be 998.7 millimeter. I think so, yeah. Simply, you have the distances. You can calculate the path for each individual wave and thereby calculate its path difference. So for wave Y, the path value was 33.3. For wave X, it was 30.8. Subtracting the two values to get the path difference, I realized that I have 5/2 as my 5/2 lambda as my path difference, telling me that this is out of phase point. When they're out of phase, they will meet destructively and hence their amplitudes will cancel off. As a general summary, superposition is basically the combination of waves at the same location. Superposition leads to interference. There's constructive interference having path differences of 1 lambda, 2 lambda, 3 lambda, and a corresponding phase difference of 2 pi, 4 pi, 6 pi. In case of constructive interference, the amplitude will always increase, whereas for destructive interference, the path differences are 1/2 lambda, 3/2 lambda, and 5/2 lambda, and a corresponding phase difference of pi, 3 pi, 5 pi. The amplitude would always decrease for a destructive interference. Moving forward, you were provided with two sources, S1 and S2. Both are light sources of frequency 12 gigahertz. Suggest what happens at X. You are provided with frequency. You are told that it is a light source. Light travels with speed of 3 into 10 to the power of 8 meter per second. And from this data, you can calculate the wavelength. The wavelength comes out to be 0.025 meter, right? There is S1 traveling a path of 0.75 meter, S2 traveling a path of 0.9 meter. And from here, you can calculate their individual paths and thereby work on a path difference value. 36 lambda minus 30 lambda gives you 6 lambda. This is an integer value, meaning to say not a decimal. Right? This simply means that the waves meet constructively because they are in phase to each other, and hence the amplitude would increase.
Sir.
Okay. Simply moving forward, I have a source S1. Okay. S1 is a source having a speed of 320 meter per second, frequency 400 hertz. Okay. You're asked suggest what happens at point X. So you need to understand that the wave travels first this path. There's also a shorter path that the wave could have had traveled, right? And definitely had traveled. So you first work out the wavelength. The wavelength comes out to be 0.8 meter. You take the individual path here and you take an additive path here, which was because of 3 meter and 4 meter, that would simply give you somewhat two paths. You subtract the two values and you will realize that your path difference comes out to be a decimal value, which means it is destructive interference and hence zero amplitude. What conditions are required for waves to interfere with one another? Please understand that the waves must definitely meet at a common point so that they could add or subtract, right? The waves must be of the same type. If you're talking about water waves, it should be water waves throughout. It should not change. Waves must travel in the same plane. the sources must be coherent sources. Now, coherent sources are the ones that maintain a constant part difference or phase difference throughout. Meaning to say, if two waves met and they met constructively, they are gonna maintain that behavior. Moving forward, you have two sources, S1 and S2. The frequency of both sources is varied simultaneously from 1000 Hertz to 4000 Hertz. Speed of the waves is 340 meter per second. Calculate the range of wavelengths produced by S1 and S2. Now, you need to understand that V is equals to F lambda, right? If my velocity is constant and I'm increasing my frequency, the wavelength should decrease. Similarly, I pick off these two ranges, and from here I could work on my wavelength values, thereby realizing that my wavelength range is somewhat 8.5 lambda to 34 lambda. So next part, longest frequency would provide you with shortest wavelength. Calculate the number of occasions at which you would expect the phenomenon of destructive interference to take place. Now you need to understand that for destructive interference, your part difference should be half lambda, 3/2 lambda, 5/2 lambda, and 7/2 lambda. Right? So you're gonna subtract. There's a path because of S1x. There's a path because of S2x. Right? There's a distance 127 being traveled from S2 till X. There's a distance being traveled 110 from S1 to X. Now this gives you a difference of 17 centimeter. You will simply equate 17 centimeter to these wavelengths, which related to destructive interference. Thereby, you would realize that from this value, half lambda is equal to 17 centimeter. Your wavelength value came out to be 34 centimeter. Right? Similarly, for 3/2, it came out to be 11.3. For 5/2, 6.8 and 4.9. You need to understand that there was a range that you had to lie in. And that range was 34 till 8.5, which is the reason why these two answers are acceptable and these will be cancelled off. Since the range of wavelengths is this value, the only two values of destructive interference lie within the range. And hence, at two occasions, you would see destructive interference. Moving forward, diffraction is basically the phenomenon in which when light travels through a small opening or an aperture or a slit, it will spread off. You could say it either spreads off or it bends. Both of these conditions telling us that diffraction has occurred. Please understand that for diffraction, your wavelength value should be comparable with the slit value. If the slit opening is very large, there would be no bending. Light travels as it is. Right? So the term diffraction refers to the bending of waves or the spreading of waves as the waves pass through a narrow gap or a small opening. This spreading phenomenon is shown in figure 1, and a simplified version of the diagram is represented in figure 2. This spreading of waves is noticeable in case of sound waves, light waves, or water waves. For significant diffraction to take place, the size of the slit must be comparable to the wavelength of the waves. During diffraction, the speed, wavelength, and frequency all remain unchanged, right? So size of the slit was not comparable here. Therefore, there was no diffraction seen. Moving forward, next comes in Young's double slit interference experiment. Please understand that for Young's double slit experiment, there are two slits. Initially, a light from a source will cause the spreading of light. And when it is incident on two different slits, having a slit spacing of A, each slit further bends the light. Could be light, could be water, could be sound. Further bending causes an interference pattern on the screen. Please note that this interference pattern has a central bright fringe, followed by first bright fringe, followed by second bright fringe, and it goes in order. Between two bright fringes, bright fringe meaning to say it's a bright result. Between two bright fringes, there is a dark fringe. Now, we use a term X, which is called the fringe separation. There's a distance D, and we basically relate all these terms X, D, A, and lambda by the formula X is equals to N lambda D upon A, where X is the vertical distance between successive two bright fringes, right? Lambda is the wavelength. D is the distance between the slit and the screen, and N is the number of orders. A is the slit separation. Right. This pattern could also be denoted by the bending part. Whenever these two lines meet, whenever these two diagrams cut each other, they will lead on to a bright fringe. But areas where there is no cutting would lead to a dark fringe. So you need to be a little vigilant here. So Young's double slit experiment, the distance between two successive bright fringes or two successive dark fringes is termed as fringe separation, which is denoted by the symbol X. Its value can be calculated using the formula X is equals to lambda D upon A, where lambda denotes the wavelengths. You could put N in here, doesn't matter, where lambda denotes the wavelengths of the wavelength of the source, D represents the distance between the double slit and the screen, and A denotes the slit separation. That is the distance between S1 and S2. Right? So let's say I am provided with a condition such that there is a wavelength 600 nanometer, this distance D, there is A slit separation. If I were asked to calculate the slit separation, I simply substituted the values. I'm just converting nanometers into meters. The distance is D, lambda D upon A, and I will get a value of fringe separation, that is from the central bright fringe to the first bright fringe. Let's say they tell you to calculate the distance between the central bright fringe to the second bright fringe. You simply multiply this value by 2. Had they said to calculate the central bright fringe to the first dark fringe, you multiply this value by half. Suggest suitable values for lambda, D, and A so that a clear interference pattern can be observed. Please understand that light lies in the region 400 nanometer to 700 nanometer. 700 nanometer is the color red. 400 nanometer is the color violet. This is your visible spectrum, right? And from here, you can work off the values.